distributed load. So this load over here is what we call evenly distributed load. Okay, so this is, then after that we're going to construct, okay, the shear force and bending moment diagrams. Some of you look at this, okay, you can construct your shear force and bending moment equation just by observation. But not all of you are trained the same, okay? What do I mean by that? Some of you go to, some of you come from different colleges or different advanced diploma. So the emphasis is not the same, okay? So I'm going to teach this in the sense that no one knows how to construct shear force diagram. No one knows how to construct bending moment diagram. So i.e. I'm taking from you guys, as in your knowledge in this topic is equal to what? 0. Okay, so I'm going to start from fundamental. Then finally, we're going to select, okay, select the beam based on bending moment. Like what I mentioned before. Okay, only. Okay, right. So, yes, anyone have question? Virus, are you okay? Okay, you're okay. So the first thing we're going to do, okay, is to find the reactions at point B and point D. Okay, so we're going to find. So I'm going to highlight. So this is number 1. Okay, so these are like step number 1. What you should be doing. Okay, cross section view matters in this case. How do you mean, Shintan Patel?
I mean, are we taking like if it's a T section or I section or something?
Yeah,
like
later on we'll do that. Okay?
Okay.
Especially when we select the beam. Okay.
Okay.
So thank you for reminding me by answering your question. Okay, so we draw a transformation first. So this is X, Y, rotation about Z. So the first thing that we're going to do is we're going to find the reaction forces. Okay, so reaction forces at point A or point B and point D. Okay, we're going to do that. Okay, so we're going to construct our free body diagram. Okay, so I'm going to sketch this out. So this is 2, 2, 4, 6, 2. Okay, so this is our point A, right? This is our point B. This is our point C, and this is our point D. Now, please observe, okay, what do I do with the free body diagram? Okay, so what are the key important points, okay, or procedure when constructing a free body diagram? Okay, because it's going to help you a lot, so you will make less mistake. Okay, so-called make it less more foolproof. Okay, so we know that we have, based on our transformation over here, X, Y, rotation about Z. We know we have a reaction over here known as BY, and then we have a reaction over here known as DY. Okay. So the first thing I usually sort out after this is my forces, right, and my equivalent load. Sorry, it's my distance and where are my equivalent load. Let me elaborate. So the distance from here to here, right? So put in your distance. Okay, so this is 0.8. Okay, so the distance from here to here is 3.2, right? And the top, you have a distance of what? 3.2. Okay, so 3.2, so 3.2. So it stops over here, right? Then you have a load coming down. Okay, so you have a load coming down. So this load is known as our equivalent load. So this will be equal to 50 times 10 to the power 3 multiplied by 3.2. Okay, so this is equal to 50 power 3 times by 3.2 is equal to 160 times 10 to the power 3 Newton. Okay, and then the next thing that we need to really like identify, okay, a lot of students don't identify this point, and that's where they make a lot of mistake, is from here to here, right? Because the distance is 3.2, you divide by 2 is 1.6, right? So the equivalent load for evenly distributed is always at the center of the section of distribution load. If it's triangle, it's L over 3. You guys know that by now. Okay. So this is our free body diagram. Then I want you to also implement this. Is your datum is always on the left hand side. Okay. Your geometric datum. Now, can anyone tell me? Okay, before can anyone tell me? Let's solve for the reaction force. Okay, let's solve at the reaction force. So I'm going to take. Okay, so we're going to solve the reaction force first. Then I'm going to ask you why is the datum on the left hand side. Okay. So once you get here, right, I'm going to state this. Okay, I'm going to find some mention about moment in the z direction. Okay, so the moment is yes.
Sorry, Eugene, why was the distance 1.6 from the left side?
Because if you look at the diagram, right, this is 2.4, this is 0.8. The total distance is what? 3.2. The equivalent load will act in the center. That's why it's 1.6. Christian, does that make sense?
Yes, thank you.
Okay, so this is why it's 1.6. If it's triangle, it's L over 3. Yes or no? Where the L over 3 is from the higher magnitude of the gradient distributed load. Okay, so I think that was covered, or I've sent a video out on that. Okay, so from here, right, so we're going to take moment at point D. The whole thing is equal to 0, right? So look at point D. So the 160 equivalent load or times 10 to the power 3 is doing a anti-clockwise direction, so it's positive. So 160 times 10 to the power 3, right? And then the distance, so the distance is equal to, so the entire length, okay, so 2.4 plus 0.8 plus 0.8 is equal to 4, okay, minus by 1.6, right? So why we take this number is because we are trying to find this distance now. Okay, we are trying to identify this distance. Okay, so because we are taking datum at point D. Sorry, our moment point D. Then after that, we have minus 3.2 by. Okay, so that is why it's so critical. I'll just show you why it's so critical to put in your known distances already. Okay, you have to do that. So from here, we have By is equal to 160 power of 3 times by 4 minus 1.6. So it's equal to 384 times 10 to the power 3. And then we're going to divide by 3.2. Let me do it again. Okay, so 4 minus 1.6 times by 160 power 3. Okay, divide by 3.2. So it's 120 kilonewton. Okay, times 10 to the power 3. Okay, then finally, to find the reaction force at point B, okay, summation of forces is positive, okay, upwards, and the whole thing, when you sum all of them up, is equal to 0. So you have 120 times 10 to the power 3 plus or minus by 160 times 10 to the power 3 plus by dy. So dy is equal to 40 times 10 to the power 3 Newton. Okay. So all these if it's positive, means the direction is correct. Okay. So all these are going upwards. Okay. Now, are you all comfortable selecting your equivalent, or not your equivalent? Are you all comfortable to say that this is upwards and this is going upwards? Are you all comfortable with that? Because one of the problems that I see quite a bit is students are having doubt to find the reaction force. Okay, so I will quickly teach you a very simple way of doing it. Okay, a very simple way of doing it. So now we know, okay, right? So if we have a reaction at point, I call this point B again, similar to I call this point B. So point B has a support and point D has a support. Okay, so I'll draw the support. Okay, so point D is exactly at the end. Okay, right? If we have a load over here, P, right? By will always be what? By will always be, or at point B, it will be going up. Okay, it will be going up. So why is it going up? Right? You ask yourself, oh yeah, it's going up. Why? Okay, this is because if you do a moment analysis, let me show you what's going on. So let's say you take a moment at point D. Okay, so we are going to take summation of moment at point D, right? So for example, now we don't know what is the reaction of By. We don't know where is By. Okay, so if you assume that By is coming down, right? That's one assumption. Okay, it's either down or up, right? So if you assume it is going down, why is it wrong? Anyone?
You will get a negative dy.
Okay, so Rajinder, you are right. Okay, I'm not saying that you're not, but a easier way of viewing this, if these two forces are going down, what will happen to the structure? If you take moment at point D, your structure will start to rotate, yes or no? Right? Your structure will start to rotate if it's coming down. If it's going up, what will happen? Will the structure start to rotate, yes or no? Anyone?
No.
Yeah. Okay. So the structure will not rotate because you got a P down here generating a clockwise rotation, right? Or anti-clockwise rotation. By, right, will be generating a clockwise rotation. So the structure will not rotate anymore. So this is where you know that this is correct. Okay. And then the next one, likewise the same. Let's say now you don't know point D. Okay, you don't know point D. So to do point D, Okay, I'm going to draw the same thing. Right? So this is your point B. So if P is coming down, okay,